Welcome to the second video on tries. In the last video, we kind of introduced what the concept of a trie was, what they were good for, and we looked at an example of a trie for a particular set of words, and we talked about how we would search for them. In this video, I want to talk about how we would add and remove. Now, adding, I have over here the beginning of a different trie. So we have our root, and as I mentioned last time, the root always points to a node. And I have a different set of words that I want us to add, and we'll add them in this order. So the way the adding operation works, it actually works very similar to a search, except it isn't just returning true or false for a contains method. It is going to potentially add new nodes. So we start at the root, and we're looking at the letter C in cat. Well, there is no child for C. So in the case of an add, what we do there is we would create a new node and have a connection from the root to this new node with the letter that we are interested in, and that's letter C. I drew that there. I am going to have to space this out because we do have a few more words in our dictionary. After the C, we're now looking at the A. Well, we just created this node. It has no children yet. So we need to create a node and create the edge. So from the node that we got to with the C, we have an edge for the letter A that goes to another node. And lastly, there is no T edge. So we create a new node and a new edge for the letter T. Now, one other thing happens here. It turns out this node, though, is now the end of a word. So we set its key value to be true. So it is a valid key if this were a map, or it is a valid entry if it is a set. So now CA, and I need to put the letter T there, cat is in our little data structure. Now I want to add cafe. Once again, we start at the root and we're looking at the first letter, C. That edge already exists. The next letter after that is A. That already exists. Now we're looking at an F. Well, we have a T, but we don't have an F. So we'll go ahead and we'll create a new node and give ourselves an edge here that points to the new node, and it's the letter F. So we're sitting on this node. Now we're looking at the letter E. Once again, we just created it, has no children yet. So we make another node and we link it in and label the connection with E. Here again, we're at the end of a word, so we set it to be true. Next word, cable. Again, start at the root, C, A. We're missing a B. So we create a new node, the edge gets added, and it has the appropriate letter on it. Up next is L, node, edge, with the letter L, and then E. Again, we're at the end of a word, so we set that to true. I'm actually going to go ahead and skip candle because I think we have enough here. Oh wait, nope, I need to do candle. Okay, C, A, we're missing the N. I'm doing it because I actually have, and let's come over here. It will wind up being significant to us in just a second. For illustrating something, C-A-N, and then the D, By the way, if you are a student of mine and I ask you to draw these data structures, I do actually want you to use this same style. D, L, and last E. Okay. That is again a key node, so it is labeled as true. Our next word is can, and this is the one that's a little bit different. C is there, A is there. N, it's present, but this is not a key node yet. So adding can is, once we get to the N, we just turn it on. Dig, just to illustrate, now we have a completely new first letter. So we start at the root, we don't have a D yet. So we make another node and link to it off of the root. And if this is dig, then next up is I. And G. And the G takes us to a key node. So I turn it on. After dig, I have did. D, I, and one new letter at the end. T, and the node is a key node. Okay, let's talk about removing. Okay, so that's how we add, and you could continue going on here. The way that you remove from a trie kind of depends upon the nature of the node, but it starts off with the same procedure. We're going to do a search. So let's pick one of our words that we have in here, and let's say we want to remove it. So let's say we remove C-A-T, cat. Okay, so we walk down the C, we walk down the A, we hit the T. And actually what our algorithm would do here is set that to false. Now, whereas all the other algorithms we could have written nicely as, but it turns out all of these algorithms work nicely recursively, but you can, for all the other ones, you could also write them as a loop. For the remove, you're probably going to want to write it recursively, and the reason is because we need to clean things up. I now have a leaf here that isn't doing anything for me. I have a leaf that's not a key node, which means it's not actually storing anything, which means it should go away. If you write this recursively, you can make it so that after it sets this to false, when it returns back up, it checks that child and it asks, are you a key node or do you have children? And if you are not a key node and you have no children, we're going to delete you. Okay, that's how we're going to clean things up. Let's remove another one from this. How about we remove can? So we start at the root, we look for the C, we look for the A, we look for the N, and since we're removing it, we set it to false. Now as we pop back up here, while this is no longer a key node, it does have stuff under it. So we don't take anything away, we just set that to false, and we're done. Just to be clear, let's go ahead and let's remove cafe. So C, A, F, E. This goes from being true to false. As I pop back up, I ask, is this child a key node or has children? The answer is no, so it's not needed anymore. From here, now I pop back up and I ask, do I still need that child anymore? The answer is no, so that goes away. When I pop up from here though, while this isn't a key node, it does still have children, so I can't delete it, and we'll just return all the way back up. So that's a quick overview of how we do insert and remove inside of a trie.